Good afternoon. I want to thank CyberScience to let me be here today. And in this talk, I will talk about a research we did in the last year at Sapienza University. This research is called SAFE, Self-Attentive Function Embedding for Binary Similarity. I hope you will enjoy my talk. So let me present myself. I'm Luca Massarelli I'm a PhD student at Sapienza University of Rome. And during my PhD, I'm trying to explore how we can leverage artificial intelligence in order to improve security. So one important task in security is, of course, reverse engineering. As other talks point out today, this is not a simple process because it requires a lot of skills, but also a lot of times, because often you have to tackle problems that are always different. And I think that if you are a reverse engineer, you know very well it, and you also drink a lot of coffee. So the field of reverse engineer is very wide, but actually in this research, we focus on a very important problem. This is the problem of binary similarity. Let me explain you. So consider that we have these two functions, function A and function B. And you want to understand if these two functions have been compiled from the same source code. You know that if I take the same C code, I can compile it with different compilers, with different optimization. And in that case, I will end up with totally different binary code. For example, function A and function B have been compiled from the same 3 lines of C code that actually perform a swap of 2 locations of an array, but function A has been compiled with optimization 0, while function B was compiled with optimization 3. So, as you can imagine, it is not trivial to understand that actually these 2 functions implement the same semantics and came from the same source code. And how we can do it? In different ways. But first, let me show you why this problem is very important. We can have at least 3 applications that will benefit from binary similarity. The first is the vulnerability detection. Imagine that you have a program or a firmware, and you want to find out if inside this firmware you have some characteristic vulnerability. What you can do is, if you are able to solve the binary similarity problem, you take a copy of the vulnerable function that we suppose you know, and you try to find function similar to that into your programs or firmware. But also, you can use binary similarity for library function identification. Let's imagine that you are a reverse engineer, you have to reverse a malware, and the writer of this malware statically linked a lot of libraries. And if the malware is stripped, as is often the case, you will lose a lot of time into analyzing, try to understand which functions came from libraries and which functions are actually typical of this malware and require more attention. So this is another important problem. Finally, you can also imagine to use binary similarity in order to hunt for malware in the wild, because if you can determine that a given function is peculiar of a given malware family, then you can try to find out if this function is inside a given sample. So we were not the first to try to solve this problem. In the past year, there have been multiple solutions, but each of these solutions presents some issue. The most famous one is probably BinDiff. BinDiff is a plugin for the famous disassembler IDA Pro, and basically what it tries to do is to compare the control flow graph of 2 binary functions, and it tries to compare this graph comparing basic blocks. And when it found that some basic blocks are different, it will point out it to the user. BinDiff is very useful if you want to analyze a patch, but it is not very useful if you want to compare similarity between a lot of functions, because comparing graph is not a scalable computation, and it will require basically impossible time to do a lot of comparison. Another nice tool that in some way solves this problem is IDA plus alert technology. This is a proprietary technology of IDA that actually is very useful when you have a 3-bit binary, and it permits you to detect library functions in this binary. The main problem of this technology is that it is signature-based, so basically it tries to look into the binary if it found some signature of a known library function. Here the problem is that using signature, you need to create a knowledge base that actually contains a copy, a very similar copy of the library functions you have in your binary. Then we have Diaphora. Diaphora is a very nice plugin. It is an open source plugin, and it is for IDA Pro and Radar 2. And actually, this plugin implements different heuristics that try to give you a similarity score between two functions. The main problem of Diaphora is that actually, if you use low heuristic, it works pretty well. But if you use fast heuristic, this does not work very well. So it can be improved. And finally, we have Yara. Yara is not actually built for binary similarity, but it is an engine in which you can write rule, and it will trigger the rule if it found some particular pattern of bytes in the binary that we are analyzing. You can imagine to use Yara to build a custom rule in order to target a specific functions. But in that case, you will require a human analyst that will write the rule. So to recap, existing solutions have three main issues. The first is the scalability. The second is that they require an exact copy of the functions you want to match. And the third one is that basically in a rule-based approach, you need analysts that write rule. But let me spend some word more about recompilation. You know that if you have a malware, it is very easy to recompile it instead of obfuscating, because when you recompile, you are sure that the application will work, but it is also very effective, because with just a careful recompilation, you can try to avoid different antivirus engines, but also you can make the life of the analyst very, very hard. And so in our research, our goal was to find out if we can make something more, and if we can build new solutions that are both efficient and effective in order to solve the binary similarity problem. And we found out that actually using some techniques that we borrow from natural language processing field is can actually give us a very good solution to this problem. So the technique we use is based on the famous model that is called word-to-vec. This is a model that has been built some years ago, and basically it permits to associate to a given word in a text an embedding vector. So let me explain what is an embedding vector. An embedding vector is actually a series of numbers, an array, you can imagine, that represents an entity. And for example, in the natural language processing field, you can build embeddings for word, sentences, or whole documents. But what is very nice of the embedding is that if I have a good model that is able to take as input words or sentences and to give as output embeddings, these embeddings actually will preserve some information of the entity they represent. For example, in the case of words, embeddings are able to represent the semantic similarity between words. To make an example, imagine that you have two words, binary and binaries. If with your word-to-vec model, you can associate to these two words two embedding vectors. This embedding vector will be not randomly. And since the word binary and binaries have a very similar meanings, when you will compute the dot product between these two embedding vectors, if the model is good, the dot product will be very close to 1. So why embeddings are so important? They are so important because basically they permit to make fast computation, because working with vectors, it's really easy and fast if you use, for example, GPU and NVIDIA, and also are very easy to share. So embeddings are a very good candidate in order to represent functions. Our idea was to associate to each binary functions an embedding vector, and then computing the similarity between the similarity between the functions using these embeddings. The idea is very simple, but the main problem is how we create this embedding, how we can train a model that is able to take as input a binary functions and to output a semantic preserving embeddings. Let me show you how does the word-to-vec model works and how we apply it to the binary code. So the idea of word-to-vec is very simple. The underlying assumption is that actually the meaning of each sentence into a text is represented also by its context. So what the word-to-vec model tries to do, it tries to predict a word inside the sentences given its context. So, for example, in the third line, the model tried to predict the word brown, given the word the quick and fox jumps. In this way, at each iteration, the model updates the embeddings of each word that are initialized randomly, and at the end of the training, we will get embeddings that actually represent very well the semantic of the word. In order to show that this works, I have this plot. And for example, if we plot the embedding of the words into a plane, we can see that this embedding preserves relationship between words. We can also imagine to ask to our model some kind of relationship. For example, the research that first developed word-to-vec model tried to answer to the model this relation. Man is to women, as king is to, and they measure that effectively the embeddings that correspond to the solution of this sort of equation was the embedding of the word queen. So if this model works very, very well, it is also able to associate to nations, their capitals, for example, and we decide to try to apply it to the binary code. So basically, we disassemble a lot of binaries, we create a very huge corpus of binaries, and we train the model over them. Basically, our model was trained in order to predict an assembly instructions given its neighbor. So when we train our model, then we also start to ask to our model some questions. For example, this one. Push RBP is to pop RBP as push RX is to, and we see that the model answers with pop RX. So the embeddings effectively represent in some ways the semantic of the instructions. We can also visualize this in 2D planes where we project the embedding of each instructions, and we see that actually these embeddings are clustered together according to the semantic of the instructions. For example, in the circle, we have embeddings that represent move instructions from the memory to the register R0, while in the triangle, we have all the instructions that represent a move from a register to a register. So these work really well, but this does not solve our problem, because our final goal is to have embedding not for instructions, but for functions. So what we need is to take the embedding of instructions and aggregate them in order to build an embedding for a whole binary functions. We tried different strategy in order to do it, and we found out that this one was the one that performed the best. Basically, what we do is we take a self-attentive recurrent neural network that I will show a bit later, and we take the list of instructions that are in a functions, and we take pair of functions. We build a dataset in which we know if two functions were similar or not, and we take pair of similar and dissimilar functions. Then we fed this pair of functions into our network, and the red layer represent actually the embedding. So we train the network using the similarity score between the two embeddings of the input pairs, and with this similarity score we build our loss functions that actually permit to the model to learn how to represent if two functions are similar or not. The model is called self-attentive because it employs a mechanism that nowadays is very common in deep learning that actually permits to the model to focus on a specific part of the input. So, for example, in our case, we see that the model focuses on the instructions that actually are conserved when you recompile a code. For example, it focuses on calls that often are conserved if you use another compiler, and in this way it learns on how to represent two functions. So the whole pipeline is this one. We take our binary functions. First, we use the instruction to vec model that we trained before, that permits us to associate to each instructions and embedding. Then we take this embedding, we fed them into our trained self-attentive recurrent neural network, and as output, we have the embedding of the input functions. So now that we have a way to compute this embedding, we want to know if actually this works. But first, let me point out something that is very important. The main problem nowadays in building deep learning techniques is that actually you need a very huge dataset. But when you want to apply deep learning to binaries, it is not difficult to have a large dataset because you can download a lot of projects from open source repository like GitHub, and you can compile it with different compilers. Each compiler has at least different optimization. You can also use different flags, and so basically you can create in few days a very large dataset. When you have a lot of binary, what you do is you take a powerful machine with some disassembler, you start to disassemble all your binaries, and you will obtain your dataset. It is important that also when you compile, you can add symbol, so it's also easy to build your ground truth. And actually, we see that in this way, these techniques works really well. In this plot, this is a receiver operating characteristic curve. Basically, this curve tells us how well a classifier is able to distinguish between the two classes. In our case, it tells us how well safe is able to distinguish between similar and dissimilar functions. If we have a perfect classifier, the area under this curve will be 1, and actually the curve will be a rectangle. But as you can see, safe, that is represented by the green curve, perform very close to the perfection. While other two solutions that we tried, one was Gemini, that was an old research paper, and the blue one was another paper that we made, perform not so well. For example, the area under the curve that in the perfect case A1 for safe was 0.99. So it is really good. But we also try to use safe to evaluate safe as a function search engine. So what we did is we take different versions of PostgreSQL, we compile it with different compilers, and we build basically a knowledge base with all the functions from Postgres. Then we select randomly some functions from this knowledge base, and we compute the embedding for the whole function in the knowledge base, and we start to query the knowledge base as a search engine searching functions using safe embedding. And we see that, for example, if we retrieve the 10 most similar functions to a query, safe is able to reach an accuracy on these 10 functions, a precision on these 10 functions of 0.9. So basically, if you retrieve 10 functions from your knowledge base, 9 of them are actually similar to your query. And I think that this is a very important, a very good and important result that actually permits safe to be at the state of the art. But what I like also of embeddings is that on top of embeddings, you can try to build different classifier. When you have a mathematical representation of an entity, basically the limit is only your creativity. So what we did is we create a new dataset where we manually classified functions according to their semantic. In our dataset, we have 4 different semantic classes that were functions that implement sorting, encryption, string manipulation, and mathematical operation. And we compiled all these functions with different compilers. We compute the embeddings for these functions with the trained model, and then we project these embeddings onto a 2D planes. And actually what we see is that, as in this figure, the embeddings are clustered together according to the functions they represent. This means that actually if I have 2 encryption functions, their embedding will be similar, and I can be able to distinguish them from 2 functions that implement a sorting. And we build on a classifier on top of it in order to evaluate also the ability on discriminating between the 4 different classes. And we see that safe as using safe embedding with a support vector machine classifier that is the basic one, we have an accuracy of 0.95, so quite near to the perfection also in this case. I like very much this application of safe because it paved the way for very interesting solution for reverse engineering that I will show you. So now this is the nice part where I will show you some application of safe, and I will start with an application of the semantic classification where we try to identify an encryption function, the encryption function of a ransomware without looking manually at it, but only using safe embedding. Then I will also show you how we can find vulnerable functions inside the firmware with safe. And finally, I will present a tool that I also presented at Black Hat this year that is Yara Safe. This is a plugin for the famous pattern matching engine Yara that actually permits you to use safe embedding inside the rule. Let's start with the first one. So our goal in this case was to try to find out if, using safe embedding, we were able to identify which functions inside the ransomware perform encryptions. So we take a sample of Tesla Crypt ransomware and we disassemble it with IDA and we compute the embeddings for all the functions we found inside it. Then we take this embedding, we apply our trainer classifier on this, and we realize that actually 6 functions of the 200 functions that were inside this sample were classified as 7 functions were classified as encryptions. So we manually look at these functions in order to understand if our classifier was right or not. And we see that 6 of them were effectively performing encryption. For example, this one, you can see that this is a performing encryption because it does a lot of math operation, and we also look at the call uses functions, but after a while we realize that actually this is a function that implements SHA-1, so effectively the classifier was able to give a very important information to the reverse engineer, that is where is the encryption function. And this application can be really useful if you imagine that you have a firmware. For example, you have an Ethernet switch and you want to analyze this firmware. If you have a methodology in order to automatically see the semantic of the function, to automatically detect the semantic of the function you find inside this firmware, you can have a sort of alert system, because let's imagine that you have this Ethernet switch, and looking at the firmware with this automatic tool, you see that there is some function that performs, for example, encryption. Why you have an encryption functions inside the Ethernet switch that whose scope is only to forward packets. This does not sound good. And so you can try to reverse engineer it hardly and try to understand what's going on. This is, I think, one of the very useful use cases for this research. Then the second one is another problem. We have always a firmware, and we want to analyze the firmware in order, for example, to understand if this firmware is affected by the Heartbleed bug or not. As we see before, often embedded systems employ all libraries, and so it is important to understand if they have some vulnerability or not. And so how we can do it? With safe is very simple, because what we need is just a functions of the Heartbleed is just a copy of the Heartbleed vulnerable functions. So what we can do is basically go to the repository of OpenSSL, clone it, compile it, and take the vulnerable function that is known and compute the embedding for these vulnerable functions. And then we can try to disassemble the firmware and compute the embedding for all the functions we find inside the firmware, and then comparing these functions with our target. If we find some candidates, probably we will analyze them manually in order to see if actually the system is vulnerable or not. But in order to make this process fast, we develop a tool on top of Yara that we call Yara Safe. So how does Yara Safe work? Basically, first of all, the analysts use a disassembler like IDA. It opens the vulnerable copy of the programs. It detects the vulnerable functions. It computes with a plugin that we develop the embedding for this function. Basically, the plugin takes the binary code, sends it to a server where the model is run, and the server answers with the embedding for the functions. Then the analysts take this embedding, put the embedding into a Yara rule, and then it starts to scan Yara, the programs that you want to analyze. Yara, what will do is to decompile, to disassemble the programs, and then it will start to query always our server in order to compute the embedding for all the functions that are inside the program. And finally, if there are some functions that actually has a similarity with the target one in the rule that is above a given threshold, the rule will be triggered. So how a Yara rule is made? Basically, first of all, a Yara Safe rule imports our module, safe. Then, what is very important is the condition. For the condition, you just call the function safe.similarity, and the argument of these functions is the embedding of the function you want to match. Then, if this embedding is above a given threshold, for example, 0.97, this rule will be triggered. So let me show you how does it works practically. In this video, I will compute the embedding for the function that is vulnerable to the Heartbleed bug. So basically now I'm loading into my disassembler the vulnerable executable that is this one. This is the function, or this is the version of OpenSSL 101A. I load it. Now I will try to detect the vulnerable function that is TLS1 process Heartbeat. I will select it, and now with a shortcut, I will compute the embedding that will appear in the console. Here I have the embedding. So what I have to do now is just copy it and paste it into my Yara rule. And now I will show you live if the rule works. So this is the rule that I have just computed. And now I will scan 3 versions of OpenSSL in order to see if they are vulnerable or not. The first one is 101A. That is the one that I use to make the rule and that luckily it will match. And after a while, now Yara is disassembling, and as you can see, the rule is triggered. And this is obvious because this is the same programs that I used to build the rule. Now I will try another version of OpenSSL that is 101E, that is the last one before the patch, so probably this is quite different from the first one, but it is still vulnerable. And as you can see, also in this case, the rule has been triggered. So also this version is affected by the bug. Finally, if I take the function OpenSSL 101U, this is a patched version, and this version does not trigger the rule. So this is not vulnerable. And what is very nice is that actually the patch is very, very small. I mean, the Heartbleed bug was caused by a buffer overflow that was solved with an if condition. And as you can see, this is the decompiled code for the vulnerable functions. There is only one if here. And if we look to the decompiled code for the patched version, you can see that we have two if conditions. So the patch was not so big, but also in this case, SAFE was able to understand which version of OpenSSL contains the patch and which version not. And finally, I want also to show how we can use SAFE to perform malware hunting. So here I have a sample of Vipassana ransomware. This is also another ransomware that we take as example in the paper. And here I prepared the rule. This rule is quite different from the previous one because in this case what I did was to combine the embedding for two functions. In that way, I hope to build a rule that will be more resilient and will be more useful when you want to use it for malware hunting. So now I will run the rule, for example, on a Vipassana sample. It will take, yes. It will take a while, less than 1 minute, because here the bottleneck is the disassembler that has to disassemble, and this sample contains a lot of functions. But then it will compute all the embeddings, and hopefully the rule will be triggered. What is nice is that actually the rule is computed totally automatically. You don't need an analyst that analyzes the sample and try to understand which part of the function change when you recompile it and use wildcard and so on. But as you can see, the rule here has been triggered. But the computation of the rule is made by the model that has learned to compute this embedding during the training stage. And with this rule, you can basically create a lot of rules to match malware automatically. And now I will try to run the same rule on something that is not the same malware, the same malware. This is a sample of the infamous WannaCry ransomware. And in this case, the rule will not match. So this is another application for function embeddings that can basically simplify the life of a reverse engineer, because the process for writing a rule is just to run a shortcut on the disassembler. And I think I'm okay. I have some time more, so if you have some question. In the meantime, if you want to leave us a star on our research on SAFE or Yara SAFE, we publish all the data sets and models on our GitHub. But also, if you want to have a look to our paper, you can download it from archive. And thank you for your attention.
Ok. Domande per Luca? Ne abbiamo? Dai, reduci, eccomi. 1, 2, ok. Inizia da qua. Arrivo.
Just a speculative question.
Yes.
If an evil malware programmer knows that his code will be checked with your safe software, theoretically, could he be able to disguise your software to write something so that your safe software will be not effective?
Yes, probably yes, of course. As every antivirus engine, you can always be tricked in some ways. There also exists a lot of techniques that are called adversarial machine learning, that actually these are techniques that, given a model, try to make it misclassifying something. And so, yes, but I have to say that there are also techniques in order to improve the resiliency to this type of attacks. We didn't employ it in our study because we start from a research question that was basically, we can compute the similarity between two functions compiled from the same source code, and we have in mind an application that was detecting vulnerable function. But actually, yes, if you imagine to the case of malware, there can be possibility in which an author try to fool your system with some adversarial technique.
Oh.
Just curiosity.
Yes.
How many people and how much time it costed the whole project?
Oh, yes. And our research group was made by 5 people. And the time was basically 1 year, the first year of my PhD. Actually, we start with an idea where we does not use a self-attentive neural network, but we use a network that was trained in a similar way, but take as input the control flow graph of a function. In our initial idea, using the control flow graph could improve the results, but then we find out that it is not in this way. Basically, if you consider the list of functions, it works well, but we realize it after a while because we spend a lot of time in order to create the dataset, build the first system, and after a while we realized that this one was the best way in order to compute similarity. But it was, I have to say that it was a really nice project, and I have worked with people that are really good, and I have really enjoyed doing this work.
Altre domande, se ce ne sono? Non vedo. Ce l'abbiamo?
Non mi sembra.
Ok, grazie Luca.
Grazie a voi.